Greetings! Welcome to Electronic Circuits 1. I am Razavi and this is lecture number 23. Today we will take a closer look at the common emitter stage with degeneration and understand some of its interesting properties. Before we go there, let's remember what we did last time. So here's a quick review of lecture 22. We looked at the gain of the simple common emitter stage a little more closely. And what we observed was that the gain is a function of the bias current in the collector and the collector resistors. And we saw that both of these can vary. For example, IC can be a function of temperatures. RC may change from batch to batch, from sample to sample. And also what was interesting is that IC itself changes with the signal amplitude. If we apply a large signal here, because the base emitter voltage changes significantly, the collector current changes significantly, the GM changes significantly, and that results in distortion. So we said let's look at another topology that might alleviate these variations to some extent. And that's what we called a common emitter stage with degeneration. Degeneration means we have a resistor connected between the emitter and ground. After analyzing the circuit, assuming that the early voltage is infinite, early effect is negligible, we arrived at a simple equation for the gain. We see that the gain is given by minus RC, the collector resistor, divided by two terms, the sum of two terms, 1 over GM and RE. So what we observe here is that this equation is less sensitive to variations than this one. Because if, for example, IC, the collector current, changes with temperature, then the effect here is a direct impact on the output, on the gain, whereas here this term is added to RE. So if RE is large enough to swamp out the variations in this term, then overall AV is less sensitive to GM variations. So today we want to pick up from here and take a closer look at these properties. So today we'll start from that. Then we will also find the input and output impedances of the common emitter stage with degeneration, whether they are the same or not as what we found for the simple common emitter stage. We don't know. We have to calculate and see. And then we'll also look at degenerated current sources, which is a natural outcome of what we study here. So let's start with some properties of the CE stage with degeneration. And we just look at this equation more carefully. So here are some observations that we can make. Number one, the gain is, okay, this pen is acting up. The gain is less sensitive to temperature and process variations and to signal amplitude. So to see this, we just write GM as IC over VT. So here we have AV is equal to minus RC, VT over IC plus RE. So this says that even though IC may vary with the signal level, because as the signal comes in, it varies this collector current, and the collector current varies to some extent, and hence the GM varies to some extent, this denominator does not change as much as when we had only 1 GM multiplied by RC. So this tells us that we can have smaller variations. In fact, you might ask, can I make the circuit very insensitive to variations in IC? Well, if I can make this term much greater than this term, then obviously variations in this term become negligible. So maybe what we can do is to minimize sensitivity to IC, right? We want this term not to be sensitive to IC, or at least to changes in IC. Well, conservatively, what we can do is pick this term to be much greater than this term. So pick RE to be much greater than VT over IC, which means we pick RE. Let me clean this up here. Which means RE times IC is much greater than VT. This is an interesting result. It says if we manage to have a DC drop across RE, DC drop, because this is just a bias current, a DC drop across RE that is much greater than VT, then this term becomes negligible. And if that's the case, we can say AV is approximately equal to minus RC over RE. So now IC doesn't have much role in this gain equation. So whatever varies IC, temperature, process, signal level, etc., has less effect on that. So that's very interesting. And for example, if we pick this to be 10 times VT, VT is 26 millivolts, so 260 millivolts of drop from here to here. 260 millivolts of DC drop will make the circuit very insensitive to IC, giving us a voltage gain equation equal to that. Okay, that's the extreme case. And also we see that if RC and RE change in the same direction, for example, they both double or they both go up by 10%, AV doesn't change. So AV is also less sensitive to variations in the resistance values. So that's a great concept that comes with the common emitter stage with degeneration. We did not have this ability in the simple common emitter stage because we didn't have RE, but now we do. By the way, we always remember the gain of the circuit as this equation, not this equation. This is only an extreme case. But in general case, that's what we have to remember. Okay, so that's an interesting result that we should always keep in mind about the common emitter stage with degeneration. The next observation that we can make is that the gain is lower with degeneration than without. Right? You can see that if RE is 0, we have no degeneration, then this absolute value is larger. So that's the price that we pay to achieve these other properties, meaning make the gain less sensitive to these variations. So we have to reduce the gain as a result of, as a byproduct of this degeneration, so that we could have less sensitivity to variations. That's the price that we have to pay. Okay, the next point that I would like to mention is the following. So just the way we verbalized the voltage gain equation for the simple common emitter stage by saying the gain is equal to minus GM times the total resistance connected between the collector and AC ground, we would like to verbalize this result as well, so that we can always apply it to more complex topologies. And again, you remember that this result was derived if the early voltage is infinite, okay? So we have neglected the effect of the RO of the transistor. All right, so how do I verbalize this? Well, this is what we will say. We say AV, the voltage gain of the circuit, is equal to minus. The minus is obvious because it flips it inverts the signal. And then what we have in the numerator is the total resistance from collector to AC ground. So that's resistance tied between collector and ground. And by ground we mean any ground, including AC ground. And in the denominator we have 1 over Gm. We'll just take that as is, 1 over Gm, plus, what does RE represent? RE represents the total resistance that we have tied between the emitter and AC ground. So we say resistance tied between emitter and ground. So long as we memorize the gain equation like so, it is much easier to apply the result when the circuit looks a little more complicated than what we have here. And we'll see examples of this in the future. So please remember this relationship. Okay, so let's talk about the input and output impedances of the stage with degeneration and see what we get. So we start with the input impedance calculation. So input impedance. So how did we calculate the input impedance? Well, we had a procedure, a well-defined, accurate procedure. We said the input impedance is obtained by first setting all independent sources in the circuit to 0. Independent sources include, for example, the battery that connects from here to ground, any other batteries that we may have, any other sources that we may have that are independent. Obviously, GM V pi is not one of those. Okay, so let's do that. And then we draw the small signal model. And conceptually, this is what we did. We said, here's our circuit. And by input impedance, we mean the impedance measured between two terminals of interest. Where are the two terminals of interest? Here. This terminal and ground, right? That's the two terminals of interest. So to do that, we set all the independent sources to 0 here. We apply a small signal voltage Vx and measure the resulting current Ix. And Vx over Ix is what we call the input impedance. Okay, let's do that for the circuit. We will draw the small signal model of the circuit. Here's R pi, Gm V pi. So R pi has a voltage of V pi across it. And then we have degeneration Re. And then here we have RC. This goes to ground, this goes to ground, and Vx also goes to ground. Again, if you're not comfortable with ground, you can always just put a wire connecting all of these together, and that would be the same thing. And we are interested in this current, Ix. Our objective is to find Vx over Ix only in terms of the circuit parameters, RC, GM, R pi, Re, etc., not in terms of V pi. V pi eventually has to vanish from our results. All right, So let's get going and see how we can solve the circuit. Maybe I'll change the color of my pen to red. Okay, our objective first is to eliminate V pi. And we just have to see how that can be done. For every circuit, the procedure might be a little different. So here we just have to look at it for a minute and see if there's a simple result that can eliminate V pi. All right, well, let's look at this V pi here across R pi. We know that the current through R pi is Ix. Ix just comes in and flows in here. So Ohm's law says that V pi is equal to Ix times R pi. Voila, that was easy. So we have Vx is equal to Ix times R pi. So, sorry, V pi. So we got our V pi, right? Okay, that's good. Now we will write a KCL here. Remember when we found the voltage gain, we also wrote a KCL here? We do that the same thing again. All right, to write the KCL here, I need to have this current, and equate the sum of the two to this current, right? How much is this current? That's Ix. How much is this current? That's GMV pi. But we have V pi. So GMV pi, I'll try to write these on the circuit schematic because I like reflecting the results on the schematic. So GMV pi is actually GM Ix R pi. Now, when you're doing these things, you have to make sure the circuit doesn't get so crowded that you will lose track of things. It's always good to use different colors, etc. And now, what is GM R pi? That's beta. So that's actually equal to beta times Ix. Is that surprising? That's not surprising because we know that if the base current is Ix, the collector current is beta Ix. So that's obvious. All right, so we have Ix flowing down R pi. Beta Ix flowing this way. They come, they unite, and then they flow through this resistor. So the current that flows through this resistor is equal to beta plus 1 times Ix. All right. If I know the current through RE, I should be able to find the voltage across RE. The voltage across RE is equal to beta plus 1 times Ix times RE. So this voltage here, I will put an arrow like this, is equal to beta plus 1 times Ix times RE. So we have found that the voltage across RE only in terms of the quantities we are interested in. We have not defined any new variables, anything else, so it's nice and clean. Okay. What other voltage equations can I write? I still haven't found Vx over Ix. Well, everything I have done so far is in terms of Ix. Somehow Vx has to come into the picture. So where does it come into the picture? Well, Vx is over here. Maybe we can try to write a KVL around this loop. So can I write a KVL around this loop? No. If you might remember from basic circuit theory, we do not write KVLs across current sources because they don't give us anything new. When you write a KVL across a current source, you get a new equation, but you also have a new unknown, so it doesn't help. But if you write a KVL in this loop, it might work, so let's try it. We start from here, say Vx is equal to this voltage, V pi. How much is V pi? Ix times R pi. So Ix times R pi plus, how much is the voltage across RE? We just found it, it's this much. So beta plus 1 times Ix times RE. And that means that Vx over Ix, which is what we call the input resistance or impedance of the circuit, is equal to R pi plus beta plus 1 times Re. So as a quick sanity check, we say, what if RE is 0? If RE is 0, the circuit reduces to the simple common emitter stage, and its impedance is R pi. Great, yeah, we know that, so not a problem there. Okay, so let's look at this result and ask one interesting question. If we had not written these equations yet, we could have asked, is the input resistance that we see from here to ground, equal to just R pi plus RE? Shouldn't it be like that? Well, that would be true only if R pi and RE were in series. Then they add together. But are they in series? The definition of series resistors or other two-terminal devices is that they carry the same current. But we know that this current and this current are not equal because of the contribution of this guy. So we cannot write the input impedance to be R pi plus RE, and of course that tells us that that's the case. Okay, so again, we verbalize this. We say the input impedance of a common emitter stage with degeneration is equal to R pi, the good old R pi that we had in the original simplified stage without degeneration, plus not just RE, but RE transformed up, boosted up by a factor of beta plus 1. So somehow, magically, this circuit takes this resistor, amplifies it, if you will, don't say amplify, multiplies it by beta plus 1, puts it in series with R pi, and then presents it at the input. So what we see at the input is R pi, this R pi, but not this RE, rather beta plus 1 times that RE. So when we place an impedance from emitter to ground, that impedance is multiplied up by beta plus 1 when we look at it from the base, when we see it from the base. All of these mean the same thing. Looking at it, seeing it, it all means this test. This is the actual mathematical test, but sometimes intuitively we say, we see this impedance, or we look into here, we see this much, etc. Okay, so that's a great result. The fact that degeneration increases the input impedance is actually quite valuable. All right, you see that it used to be R pi, but now it's higher. Okay, let's see if we should move on to the output impedance. Yes, let's do that. So we go to the output impedance now. And again, the assumption is that the early voltage is infinite, as was the case before. So we don't have RO of the device here. Let's try to find the output impedance. What does the output impedance procedure look like? Well, we said that we take the circuit, we set at its output. So the output as a port, meaning two terminals of interest. And we kill all the independent sources in there. We set them to 0. All the voltage sources become short circuits. All the current sources become open circuits, including the input voltage source. Presumably, the circuit is driven by an input voltage source, right? This voltage source here. So that voltage source has to be set to 0. And now we go to the output, and we apply a voltage source Vx, measure a current, and that would be the output impedance. Do these procedures look the same or not? They look the same, but there's one subtle difference between the two that one must not forget. We applied this voltage to the input of the circuit. What did we do with the output of the circuit in this test? We didn't do anything. We left it open. The output is this node here. This node here was left open. We didn't do anything here. Right? That's just there. Whereas in this test, we applied the voltage to the output. So we applied here, but because the input is driven by a voltage source, that voltage source has to be 0. So we put a short circuit here. So here we have a short circuit, here we don't have a short circuit. That's the difference between these two calculations. Okay, so let's draw the small signal model following this procedure by shorting the input. So we short the input, we apply the small signal model of the device, GMV pi, then we have RE, and we have a short circuit here, and then we have VX, IX, and these are all connected to ground, so we just connect them together. It doesn't really matter. And again, we first try to eliminate V pi and then find Vx over Ix. Okay, so how does this work? Where do we start? Let's change the color and see. Now, this happens in some circuits, so it's good to remember that once and for all. Let's examine the voltage across R pi. R pi has a voltage of V pi on it, with its positive terminal up here, negative terminal down here, right? Okay, how much is the voltage across RE? Well, RE and R pi actually seem in parallel, don't they? These two terminals are shared, and these two terminals are shared. So they are in parallel, which means they should have the same voltage on them. That's fine, yes, that's true. But I am really interested in the voltage across RE with a positive here and a negative here for other equations that I will write. So if I denote the voltage across RE as shown here, how much is that voltage? Is that V pi? No, that's minus V pi, because V pi has its negative here and its positive here. So this will be minus V pi. Okay, so let's write a KCL at the emitter node, just like before. Our KCL is, the current coming down R pi is V pi over R pi. V pi over R pi. Coming down here is GM V pi. And these have to add up to how much? The current through this guy, which is its voltage divided by the resistance, minus V pi over RE. Okay, how much is V pi? Well, because R pi and GM and RE are not under our control, the only possible solution here is for V pi to be 0. There's no other solution. So V pi is 0. If V pi is 0, how much is GMV pi? That's 0. If GMV pi is 0, what do we do with this? It's an open circuit. We throw it away, right? It's an open circuit from here on. So, sorry, I forgot to draw RC. Let me draw RC in red, so that we avoid any confusion here. That's RC. So, going back to brown. So we see that this is an open circuit. All of this is thrown away. We just have RC. So IX has to flow through RC because GNV pi is 0. That means that Vx over Ix is equal to RC, nothing else. So Vx over Ix is equal to RC. So the output impedance of the common emitter stage with or without degeneration is equal to RC so long as this condition holds. All right, that's important to remember. In all of these calculations, we have assumed that the early voltage is infinite. So let's summarize everything that we have found about this circuit. That's what we do. We say, we draw the circuit like this in a very simple form, and we write our assumption to make sure we don't forget. And we say the gain is this much. Then we say the input impedance, again I use an arrow to indicate that. The input impedance is equal to R pi plus beta plus 1 times Re. And the output impedance, I put an arrow here, is equal to Rc. This is the image that needs to be imprinted on your mind for the rest of your life for the common emitter stage with degeneration. Input impedance, output impedance, voltage gain, and what the circuit looks like under this condition. All right, so that is the result of our analysis. Okay, let's, based on these, let's go over a quiz. So I will need to add a new page. I hope you have taken notes of everything. Let's go add a new page, and let's see what our quiz is today. We start out with our simple common emitter stage with degeneration. Here's the circuit, RC, RE, Q1. And we use this as a pre-amplifier for another amplifier. So I bought an amplifier in a box, and it turned out that this amplifier didn't have enough gain. So I decided to place a pre-amplifier before this amplifier. And it just happens that this amplifier, at its input, has another common emitter stage with degeneration. I won't bother drawing everything else. I just draw this little part here. So our preamplifier is over here, and our main amplifier is here. So that's what we call main amplifier. Okay, so here's the overall environment. And what we would like to do is calculate the voltage gain of the preamplifier by itself. So from here to here, before we connect the main amplifier and after we connect the main amplifier. So before we connect the main amplifier, it's obvious, right? If this guy is not here, the gain is just R minus RC divided by 1 over GM1 plus RE. So the question is, now that I connect this amplifier, I load the preamplifier with the main amplifier, what happens to this gain? We expect that the gain will go down. And the question is, what does the gain equation look like? I will give you 90 seconds to do it. Okay, so what did you get? Well, let's remember the equation for the gain of a common emitter stage with degeneration. This is how we verbalize it, if you remember. Let's go back and see what we said. We said the gain is equal to minus the resistance tied between collector and ground in the numerator. And then 1 over Gm plus the resistance tied between emitter and ground in the denominator, right? So let's see. What do we have here? We're going to apply that principle to this circuit. So we will write AV is equal to minus the resistance seen in the collector, the resistance tied between the collector and AC ground. Okay, so we have RC here, RC. But is that the only resistance tied between the collector of Q1 and ground? No. Something else is going on here. Certainly this base draws some current, some AC current when there's signal, right? So that has to be reflected in this equation. And in fact, the current that's drawn here, if you divide this voltage by that current, we find the input impedance of the circuit, right? So what we should place in parallel with RC1 is RC is the input impedance of the next stage, because the input impedance is between this point and AC ground. That's how we measure it. And RC is between this point and AC ground. And both of these go from the collector of Q1 to ground. So this should be in parallel with R in 2. R in 2, in a sense, is the impedance that we see looking this way. R in 2. The impedance, the input impedance of the second stage. All right, and then in the denominator, we have the same situation as before, so not a big deal. We have 1 over Gm1 plus Re. Okay, so all I need to do is calculate R in 2, place it in parallel with RC, and I'm all set. So let's do that. Let me erase this a little bit. And now we write it here, say minus RC in parallel with the input impedance of the second stage, the input impedance of a common emitter stage with degeneration. How much is that? So that's why all of these equations have to be readily available in your mind so that you can quickly write them down. You have to memorize all of these equations. So we verbalized the input impedance of a common emitter stage with degeneration as R pi plus beta plus 1 times the impedance in the emitter. Right? That was our equation for the common emitter stage input impedance when we have degeneration, as you remember from here. So now these apply to the second stage. So this would be R pi 2, this would be beta 2, and this would be Re2. So we go and place those in here, and what we get is R pi 2 plus beta 2 plus 1 times Re2, and then the denominator is the same as before, 1 over Gm1 plus Re. And that's it. We have found the voltage gain of the first stage when the second stage, when the main amplifier is loading it. If this amplifier were not here, then all of this would be gone. We would have only RC divided by all of that. So obviously, the presence of the main amplifier has reduced the gain by introducing this impedance in parallel with RC. All right, so that is the equation that we have found. One purpose of this example was to show you that if we don't have this intuition about the input impedance, the gain, output impedance, everything else, then as the circuits become more and more complex, we will be totally crippled with lots of equations. So yes, maybe we can even work through the equations and solve them and find an answer, but the answer would be gigantic. Because if you didn't know any of this stuff and you wrote this, imagine what this would look like, right? Because this parallel sign wouldn't appear in your equations, perhaps, right? You would have RC times this mass divided by RC plus this mass divided by this. So it would be a huge equation. But now we have a much better view of what is going on in the circuit. Okay, that was the quiz. We now go to the next topic, which is dealing with current sources. So let me change the color of my pen, and we start out by this. We say, let's build a constant current source. Right? You need a constant current source for some circuit. Maybe you haven't seen why you need a constant current source, but that's okay. We'll see it later. Someone says, can you build me a 1 milliampere current source? What do we do? Well, we saw earlier on that a bipolar transistor in the forward active region can operate as a constant current source. And the way we analyzed it and came up with that idea was we had a bipolar device. After we biased it by means of a battery of some value, let's say V0, we observed that if we put this in a box and give it to somebody, and that person varies this voltage and measures this current, he or she observes that the current is relatively constant. And that's the definition of a constant current source. So what we saw was that if we apply some sort of voltage here, so maybe call it V1, and sweep this and measure I1. So let's sweep V1 from 1 volt to 2 volts, that's V1, and then see how I1 varies. We saw that without early effect in the ideal case, I1 was constant, as long as we haven't fallen into saturation. And but when we did have early effect, this current started varying by a little bit. So let's change the color to blue. So we saw that with early effect, looks like this, right? So here the early voltage is less than infinity. Here the early voltage is infinity. All right. So that's a current source that we can build and give to anybody who needs it. But something interesting happens if, in this current source, we degenerate the emitter by a resistor. So let's look at that. Let me go back to this color and see what we get. So I will draw the circuit like before, but add a resistor in the emitter. And same situation as before, some sort of voltage. We don't know how much, but however much is necessary. There's a resistor here. We put this in a box, and we deliver this as a constant current source. So the person runs the same test. We apply a variable voltage source here and measure the current, and we plot it. And we're wondering what we're going to get. Okay, well, let's say there is no early effect. So consider the case of VA equals infinity. Well, if there's no early effect, when the collective voltage goes up and down, the current just doesn't change. Doesn't matter what we have here. Remember that if there's no early effect, it means that the base width of the device doesn't change with the collector voltage, so the current is always the same. So with an infinite early voltage, we have a constant straight line like before, so nothing exciting yet. But if we consider a finite early voltage, what happens exactly? So again, I'll change the color to blue, and I assume VA is less than infinity. And what we'd like to see is whether this varies or not, and by how much. So is this situation better or worse than this situation? And by that I mean, do we have less variation or more variation? That's what we would like to find out. Okay, so how do we exactly analyze this? How do we exactly answer this question? Well, there's a nice and simple way. What we do is we go in here and consider a narrow range for V1. So we say V1 varies by only a small amount. V1 varies by, let's say, 10 millivolts. Okay? And now we go and look at the variation of I1 as a result of that change. So here versus here. So if for a given voltage change here we have less current change in the second case, then the second case has a more constant current, which means it's a better current source, or the other way around. So that's something we have to analyze. Now, because we confined the variation of V1 to a small range, we can go and utilize the small signal model of the device, because the small signal model represents small variations in voltages and currents. So we can do that. And this time, because we are using the small signal model, and because we are interested in the early voltage less than infinity, we have to include RO of the device as well. So here's our objective. We have a circuit like this. Maybe I'll just draw the small signal model. I think that's clearer. So we are changing the collector voltage by a small amount. We're going to draw the small signal model of the circuit. We start out with the battery here. That battery goes to 0 because its value doesn't change. Then we have the transistor itself. So that's R pi and GMV pi plus minus V pi, GMV pi, and then RO, of course, because we are interested in the non-ideal case. We have degeneration, RE, going to ground, and we are setting this battery to 0 because its value doesn't change, so that's a short circuit to ground. And now we would like to see, for a given change here, how much current change we get. So that means we apply a small signal voltage source here, we call it V1, and measure the small signal current flowing, which we call I1. I1, little I1, represents the change in big I1. Little V1 represents the change in big V1. So that circuit, as you can see, is actually finding the output impedance of the circuit. Wasn't the definition of output impedance the same? We said put the whole circuit in a box, kill all the independent sources, apply Vx, measure Ix. This time we just call it V1 and I1, but it's the same thing. All right, so we need to analyze the circuit. The difference between this circuit and what we studied before is that now we have this RO. So that makes things a little more complicated. So if we compare that with what we had on the previous page in calculating the output impedance, see here we applied Vx and measured Ix. We had everything else. This point was grounded, but we did not have RO. So this result which we obtained is not applicable to our new circuit. So let's go back to our new circuit and see what we should do. All right, let's see. Okay. Again, my first attempt would be to eliminate V pi and then try to express V1 in terms of I1 or something and find V1 over I1. All right, well, do we see anything familiar here? The top terminal of R pi is grounded. The bottom terminal of RE is grounded. The bottom terminal of R pi goes to the top terminal of RE. So R pi and RE are in parallel. So what is the voltage across RE? If I'm interested in positive here and negative here, this would be minus V pi, just like before. All right, that's good. We got that. Okay, so now we have to make another interesting observation, for which I will change the color of my pen to maybe brown again, or red again. All right, so let's see, and let's start from here. A current of I1 is flowing this way. It comes to this point and splits. Some of it goes this way, some of it goes this way. But then what happens? This current and this current reunite here, and they exit this wire. So can I say that the current going through this wire is the same as the current here? Yes, because the current cannot disappear. Whatever we push into this node has to come out of this wire. So we can say that this current is equal to I1. Okay, now can this simplify our analysis? Well, yes, because I can write a KCL at this node, including this current, and this current, and eliminate V pi. So let's do that. How much is the current coming down this way? That would be minus V pi over R pi. How much is this current? I1 plus I1. I'm sorry, this is plus V pi over R pi. Then plus I1, that's this current. And then the current flowing through RE downward is minus V pi over RE. This current plus this current must be equal to this current. So that's equal to minus V pi over RE. We are interested in V pi, so let's bring V pi, that term to the left, take I1 to the right, or the other way around, and we write this as minus V pi over 1 over R pi plus 1 over RE equals Ix. We immediately recognize the parallel combination of R pi and RE. Of course, because they are in parallel. So we can say that minus V pi is equal to Ix times R pi in parallel to RE. All right, so we found V pi. That's great. Let's go ahead and solve the circuit. Okay, so what else can I write? Well, of course, I need something in terms of V1, because I'm interested in V1 over I1, which means I should probably write a KVL like so. I have to write a KVL including V1, because I need V1, then including RO, not including GMV pi, because we do not write KVLs across current sources. So it has to include RO, then it has to include RE. The only problem is RO, because I do not know the voltage across RO. And again, I'm resisting the temptation to introduce new variables. The current through RO, voltage across RO, etc. I'm just trying to use whatever I have here to find the current through RO. Okay, well, what we know is that I1 comes in, but we lose some of it before it flows through RO. How much do we lose? We lose GMV pi, but we have V pi. So the current that goes this way is equal to GM times this with a negative sign. So that's minus GM Ix R pi in parallel with RE. So it's good to write these on the schematic so that we can keep track of them. All right, so then how much is this current? Well, I1 comes in, we lose that much, and the rest flows through this. So we have I1 minus all of this. So plus GM Ix R pi in parallel with RE. So we found the current through RO. That's great in terms of Ix. in terms of Ix, right? So, sorry, I1. This is all I1. At some point, I think I called these, I'm sorry, this is I1, this is also I1, and that's also I1. Okay, so now we can find the voltage drop across RO by simply multiplying the current through the resistor by the resistor. So now we are ready to write our KVL. KVL says this voltage is equal to this voltage plus this voltage. So we can write V1, this voltage, is equal to this voltage, which is equal to RO times its current. So RO times its current, I1 plus GM R pi in parallel with RE times I1. So V1, this voltage is equal to this voltage plus this voltage. How much is this voltage? Minus V pi. We have minus V pi. Minus V pi is this. So plus I1 times R pi in parallel with RE. So now we can find V1 over I1. And that is the resistance that we measure there. So V1 over I1 is equal to 1 plus GM R pi in parallel with RE times RO plus R pi in parallel with RE by itself. Okay, so does this tell us anything about what we were curious about? Remember here, we went through all of this because we were curious to see if the current variation here is smaller or larger than here, with degeneration and without degeneration. Which one is a better current source? Okay, well, we know what's going on here. We know that the ratio of this voltage change over this current change is how much? It's just RO, right? RO is the inverse slope of this characteristic. So that's just RO. The impedance that we see between these terminals, the small signal impedance, is RO, RO of the transistor. But how about here? We see that the voltage change divided by the current change gave us something like this. Is this greater than RO? Sure, we have RO times 1 and then some other stuff. So it's higher. Because the voltage over current, voltage change over current change is higher, it means for a given voltage change, we have a smaller current change. For a given voltage change, we have a smaller current change. So this is a flatter characteristic than this one. So it's a better current source. Okay. This equation plays a critical role in many circuits that we will study in this course and other courses. So it's very important for us to get absolutely comfortable with this equation. This equation tells us that if we have a degenerated bipolar device and we find the impedance between these two terminals, right? This is what we did, impedance between these terminals. What's going on at the base? Well, the base has a battery on it for now, but it doesn't matter. It's AC ground. This is RE. And what this equation says, which we will call this R out, is what we measure between these two terminals here, from here to ground. So we'll have a shorthand for that. We'll draw an arrow like this, and we'll say R out is equal to this equation. I hope that's not confusing. So when we say R out is this much, we really mean that a test was conducted by applying a voltage source from this terminal to this terminal and measuring the resulting current, even though we just write it in abbreviated form like this. Okay, let's play with this equation a little more to make it something perhaps memorable. So we will write R out is equal to, I will regroup these. So here I have GMRO times this parallel combination, and here I have the parallel combination. So I can factor out the parallel combination and write it like this: 1 plus GMRO times R pi in parallel with RE. And then the only thing that remains is this RO times 1. So plus RO. This equation is a little more palatable than the other one, so I usually memorize it like this, but you can also memorize it like that. So this equation says, if we had no degeneration, if RE were 0, this is 0, this whole thing is 0, we get RO. So that would be this case. You just have a simple current source like that, and you look into here, and you see RO. Right, obviously, because that's the small signal impedance between collector and emitter. But once we added emitter degeneration, this impedance is no longer RO, and it's not even RO plus RE. It's not RO plus RE. Why? Again, because these two are not in series. Something else is going on here, right? So this is not in series. You can't just say these two are added. Something much more profound happens as a result of degeneration. What we see is that the impedance at this point is, for example, if you want to look at it as RO, but RO multiplied by a relatively large number, perhaps. Okay, and then plus some other stuff. Now, if you look at it this way, this is how I interpret it for myself. I say, the impedance that we see at the collector of this degenerated current source is equal to R pi in parallel with RE. Do we know what that means? Well, that sort of is here. Remember, we found out that R pi and RE were equal. We had them all over the place. So if I sit at this emitter, I see an R pi this way and RE this way. So R pi in parallel with RE, that's somewhat easy to remember. Boosted up by 1 plus GMRO. And GMRO is what we call the intrinsic gain of the transistor. So R pi goes in parallel with RE, and then it gets boosted up by 1 plus the intrinsic gain. And then to that, we add RO. So this seems redundant, all these explanations and so on, but you will see that once the circuit becomes more and more complex, this verbalizing of the result is very helpful. So that's what we need to remember. Okay, so our time is up. Next time we'll look at this a little more carefully and then go to biasing techniques for the common emitter stage. I will see you next time.